Okay, it's hard to believe we are down to 1 week of classes left. Kind of hard to believe. Here's the schedule. Today we've got what I would say is the last of the new material that's going to be covered on the final. Wednesday we've got a Comp 40 preview. Like I think I said the other day, if you're taking Comp 40, I strongly suggest you come to that lecture or at least watch the video. If you're not taking Comp 40, it will not be bad information. It will just be geared more towards people taking Comp 40. We're still going to talk about some interesting things. It's not like just going to be like an overview, but it's going to be some interesting things. So, but you're not, certainly it's not going to be on the final, so that's that. And then next Monday, which is the last class, we will have a review, kind of like with the review we had for the mid-year exam, or midterm exam. Okay, did everybody get the email about the final, what was it, did everybody get the email about the final evaluations for the course? Did you get emails about that? Check your email. Maybe they're sending out in waves or something. But if you did in lab, you'll be doing those. You can do them before lab if you want. But I'd like you to get them done in lab just so we know. The more people we get to do the evals, the better for the department, I think, in general. All right. Any questions? So before I get going. Yes, Yanni. OK, so the final for this class is a week from Friday. Is that what we decided? Somebody told me earlier, a week from Friday. I'll have more details later. It's probably going to be in here, although I hope not, because this is a crammed room already. And some people from the other section want to take it. If you want to take the late exam, if you want to stick around all the way until it's like the following Friday or something crazy like that. If you want to stick around then, you're welcome to take the late exam. If you've got a lot right at the beginning and you want to take the late one, you're welcome to. That room's big enough for everybody. It's the other way around that I'm a little worried about. Question? Is that your question? Yeah. I'll probably send out a little thing about people asking people to say whether or not they're going to try to go to one or the other. Yeah.
I was going to say, do we when do we have to give you our final of which one we're going to?
I'm not too worried about it. I mean, when you can, the answer there. OK. Anything else? All right. Anybody know who this guy is? You should. Donald Knuth. Did it say it up there somewhere, or are you just that good? Oh, it says right there. You guys are good, though, right? No, this is probably one of the most famous computer scientists in the history of computer science. I'm going to show you a tiny little clip later. He's going to talk about some of the things we're going to talk about later today. He's kind of getting up in years. He's not. I think he's mentally just as sharp, but I think there's some other things. He's stuttering a little these days, and he's but he's still brilliant guy. I'll tell you a little more about him later. Okay. Let's see. Here is what we are going to do today. I'll mention a couple things about the final project again, and then we'll talk about 2 more data structures. I will not make you know that much about these. Like, I kind of want an overview thing. I'm not going to make you come up with some algorithm for ropes or binary decision diagrams, but I'll probably ask 1 or 2 fairly broad questions on those on the final. Okay. How's song search coming along? Yeah, it's coming all right. Hopefully you guys got a little time to work on it over the break. If you didn't, then you probably need to step it up unless you're already done or whatever. There's a couple people who are done, for what it's worth. Provide is up. I'm getting some reports that there might be a couple bugs in Provide, and I will try to check that out. Thank you to those who've emailed me about those. And then, did anyone see the email about the online tester I have set up? Or it was a Piazza thing. So this is a thing you can go to, www.cs.tufts.edu/comp15 song search _web. And it's just mine that I put online. And it's you can search for things like finicky. Is that how you spell finicky? CKY? Like that? Yeah. Something like that. Anyway, and then it searches, and hopefully nobody broke it, and there you go. So there's two things there. Any bad words? There's a bad word. How did that happen? Let's try another. Let's try a different one. Persnickety. Nothing. OK, well, anyway. Anyway. A-N-Y. Anyway. All right, there you go. OK, so any bad words up there? All right, so you can see it's just a search, and this is the full database. So what I've done is I've got my full database program running on the computer in my office, and you can go and type in whatever searches you want in there, and it should be what we're expecting from you. So you can test out the big database. If you want, I can put the small database up too. I don't know if anybody cares about any of those. But email me if you do, and I'll set that up. Now, 2 comments on this. First of all, for the people who did see this, you guys ever heard of log files? So you know how Google makes all their money? 2 ways. Google makes their money how? What ways does Google make their money? Yeah. Ads. OK, so they serve you an ad, and hopefully you're going to buy something based on that ad. Very few people do, but they only need this many people out of the billions of people that look at ads to actually buy something, et cetera. Well, or to click on it, right? And then how do they know which ads to give you?
They know your personal information.
They watch your searches, right? So if you type anyway, right, they're going to give you something based on like the anyway whatever, right? They're going to like serve these things, right? So I have a back end which I was using in part of the testing is to make sure that the words are coming through, right? So I just have it print out all the search words. Keep that in mind when you do your searches, people, because some of you have already searched for words that I wouldn't say are good for polite company. Just so you know. That's what log files are, right? They keep everything you type into the search engine. So just so you know. OK. And I only mention that so my eyes don't bleed when I go back and look at the log. Here's the website again for those of you who care. wcs.tufts.edu comp15 song search _web. And that should come up. And I blatantly, obviously, stole from another search engine for the logo. Alta Vista. Yeah. All right. Questions on that? Any other questions on the final project? Anything else come up? Yeah.
I know you said it before, and I don't remember. How do you figure out how much space you're taking up?
There's a time function you can use, or there's a function called htop, which I'd search for time in Piazza, it'll tell you. Anything else?
Wait, it was song search _web?
Underscore web, a lot lowercase. Yeah. All right. OK. So that's song search. It's due next, what did I say, Sunday? I think Sunday. OK. We'll have lots of TAs this week, hopefully. And by the end of the week, I'll start spending more time in the lab, too. Yeah.
Okay. I think we mentioned this before. I've been struggling with vectors a little bit.
Struggling with vectors. OK.
And I think I'm still having trouble understanding the role of the iterator. I understand that there's a pointer to a spot of the vector.
Yeah, the iterator just allows you to walk through the vector one thing at a time. That's all the iterator's for, really. And so if you have specific questions about the vector, feel free to stop by. I'll chat with you about it. All right?
So far, I don't think I've been using it at all.
OK. If you haven't used it yet, then if you start having problems with it, sounds good. Yeah?
I have a question on like the vectors and like, do you have to delete a vector? I was kind of confused on that.
If you use the word new, you need to delete whatever you newed. Right? Right? If you didn't use the word new, then you don't need to delete it. So if you just say vector, right, string, my vec, did I use the word new? No, then I don't need to delete that one. If I say, let's say vector string my vec, I would have to be a pointer to it if you were going to use you or new. My vec equals new vector string, right? Then you would have to delete it.
Then you would just say delete my vec.
Delete my vec. Yeah. Yep. That's all. And then under the covers, it knows to do the delete with the brackets for the thing and all that. You just say delete that. Yeah.
I had trouble with that. I read that the way to do it is with the clear command.
Never heard of the clear command.
Clears out the vector. It
OK.
it doesn't delete the vector. It just deletes what you put in the vector.
OK. So you don't need to use clear. It will go and the vector will go and delete everything in there for you.
So clear is insufficient?
Right. Clear is insufficient to delete the vector. Yeah. No big deal. It's not hard to fix. Yeah.
When you're implementing a try, so the constructor you'll use new node as another class.
Uh-huh.
But in the destructor you don't delete anything. That's when it's
No, you would have to delete it. If you use the word new, you have to go through and delete. Now, if you've got a try and every little one of those tries has a different one that you've newed in it, you need to go and like walk through the whole try and delete each one individually. OK? It's tricky to do. Now, with a try, it's not so bad because you can walk through a try fairly easily. It takes a little time, but it's not that hard to do. Yeah, not that hard. Now, that's only if you ended up using the new keyword for that particular piece. if you didn't, then you could, like if you have new for all your songs, you can delete all the, you can go walk to the vector and delete all the songs. But that probably won't go and delete the individual like try. Yeah. All right. Anything else, Nathan?
Two things. First, I think the reason that was questioned is there was no destructor in the try lab, but we have memory.
Oh, there was no destructor in the trilab, yeah.
It wasn't written.
Right.
We have to write it now. So my actual question is there a good way to find the, well, first empty space in a vector, like vector.length?
Is there a good way to find the empty space in a vector? No. You probably should walk through the whole vector.
No, as in like the
You mean-
end of the vector where you should insert anything.
Oh, yeah, well, the name, your variable name dot end parenthesis parenthesis will give you the last one. But that doesn't necessarily give you the capacity. You can figure that stuff out. It's just not recommended that you ever do, just because you don't normally need to. Now, if you're going to try to implement a hash table with a vector, you can do it. I just wouldn't suggest doing it.
So then how do I insert something at the end of a vector?
Right, you do push back, right? And then you have an index. And that index you can get by either doing, well, the easiest way to do it is to get the index of length minus 1. So the vector, the variable name dot length minus 1.
Push back, just know to put it at the back.
Oh, sorry, push back knows to put it right at the back. Sorry, I'm thinking insert. You're right. Push back actually pushes it right at the back. Thank you. Yeah, so you don't need to do anything for pushback. Yeah. Did that answer your question? OK, cool. Anybody else? All right. All right, so that's that. Let's go into two more data structures. So again, we're kind of going down this road of data structures that are interesting and slightly more advanced than other like basic ones, right? The basic ones are the ones that everybody's expecting you to know. But the ones that we're talking about now are the ones that you can either wow people with in interviews or you can just know for future programs that might make your programs more efficient. Okay? Speaking of interviews, if anybody does have if after you finish the song search and it works, right? If you get an interview and you might want to like tell whoever you're interviewing with, hey, I created this cool song search thing. You can put the binary online like I did here, right, with the song search here. I can show you guys how to do that so that it comes up so that you can send somebody and say, hey, go check out my song search thing, and they can go type in things, right? You might want to get the bad words out of the dictionary, but otherwise you could show them that.
Should we not plagiarize
Okay.
Google?
You what? You probably can't. Yeah, you probably shouldn't plagiarize Google. But then again, they wouldn't really care. I don't think they'd care that much, unless it was Google. No, they might even like it. I don't know. Who knows? They probably wouldn't. All right. OK. So anyway, what's that?
Just plagiarize Bible.
There you go. Plagiarize it.
Copyright
All right.
system.
Yeah. All right. So we're going to start out talking today about, and we're going to go through these kind of quickly. There's only two more, right? We're going to talk about this thing called a rope. Okay, a rope is this interesting data structure that's used instead of using a regular old string. Okay, if you're ever writing your own editor, like text editor or word processor or something, you might want to consider using these things called ropes. Okay. Normally, when we store a string, and you guys all know this by now, right? When we store a string, it's basically stored in an array where the first line in the first letter in the string is at position 0, and the last one, it just goes one position after the other all the way to the end, right? And then if you want to, like, let's say you want to insert into this between the, let's say between the V and the E here, and the quick fox jumps over the dog, how would we insert right there? Like, what would we have to do for a string?
Put the new word in, you'd have to move everything.
Did you raise your hand? Well, go ahead, Charlie. You said you'd you'd do what? No. Go ahead.
You put the string in, you got to move everything else.
Well, OK. So yeah, you would have to move everything over if you wanted to do it that way. But even more so, let's say this was the end of your array. You'd have to create a whole new array, right? Copy all the piece up to where you want to go, and copy the new piece in, copy the rest of it, and be done. And then, so there's a lot of stuff going on there. Either you're moving stuff, which is in itself kind of annoying, or you're doing something even worse, which is creating a whole new vector or array, copying everything over, and going from there. So it's definitely a little bit more like it's a little bit intense to deal with a long string. And think about this. Let's say you're writing your PhD dissertation and it's like 200 pages long, right? And you've got would you have one long string in there, right? It probably is going to be a little bit slow if you're trying to do lots of copy and paste. And this is perfect for copy and paste, right? If I take the over and I copy it and put it right after the quick, right? Well, we don't want that to be like, OK, create a new string, move everything over, move out, you know. There's lots of stuff going on there. I suppose copy and paste could be, you could make that a little more efficient by like just saving this if you knew you were going to paste, but who knows, right? So strings have some issues dealing with this, especially when you get into long strings. Short strings, who cares about? But it's the long strings, like in a text editor, that you might start to care about. OK? So this is what we were saying. This doesn't make it easy to insert. Break the whole string, recreate a new string, et cetera, et cetera. All right? Well, take a look at this data structure. This is called a rope. OK? And maybe you can figure out why it's called a rope in a second. But what happens is, what you do is you actually kind of create a binary tree out of the pieces of your string. Okay? You can create these a number of different ways. I didn't really find a canonical way of creating them, like a way that everybody uses to create them. But you could start out with a long string, and then you could break it into a rope like as time goes by. Or you could go and take a long string and convert it into a rope using an algorithm that just breaks it into pieces. But here's what it is, right? It's a binary tree. The text is always at leaves, right? And if you walk this in order, you end up printing out the string, right? So you go down here and you walk it like this, and the quick brown, and you go over here. Fox jumps over the lazy dog, and you end up walking through it and doing that, right? Anybody want to guess what the numbers in there stand for? What's that? How many characters? OK. So that's true that Fox jumps over the with all these. I just put these underscores for the spaces in here. That's 19 characters right there. And this is 5. What's the 19 here stand for?
The maximum characters and such.
Good idea. Maximum characters. It's not. Notice the 19's always, it's always which one? Well, you can't really tell here. How much stuff is to the left? Right? That's because in a few minutes we'll figure out how to find a certain position in this string, and you need to know some information about that in order to do it, unless you want to walk through the whole thing, right? So it's kind of clever the way we use that. But what it is a node has the number of characters in itself, if it's a leaf, or the number of characters in its left-hand path of the tree. So this one, 24, is going to be 19 and 5, right? And the 19 is just going to be the 19, and the 16 is going to be the 10 and the 6, et cetera. See how that works? So it's kind of clever, and you'll see why it's clever in a minute. But you also see why this is kind of called a rope, because it looks like there's like pieces here that are kind of floating around and all kind of attached like one long rope. Okay? That's kind of neat. Okay? Like I said, strings are only kept on leaves, and we already talked about how you'd figure out the weights. Okay? All right, so how do you search for a character? Using that information, how might you search for a character? It's actually an algorithm. It says right here. But there's an algorithm that actually shows you how to do this. I'll walk you through the algorithm instead of like telling on the next page is actually the algorithm itself. If we want to search for character 21, which happens to be the J right here, you can't necessarily search for the actual character. Like if you want to do a search of the characters, you kind of do have to do a regular old linear search in this case. Not much else you can do about that. But if you want to find the actual position, if you happen to know the position you're jumping to, right, then if in this case J is 21, well, we start out and we use this information we have, right? We say, OK, the root is 16, and 16 is less than 21. Now what that means is there's 16 characters to this side of this node, so we know we're going to have to go this way. That just kind of makes sense, like in general, right? And that's what's nice about this. Well, what you have to do though is you have to say, OK, look, I'm getting rid of 16 of them, so subtract 16 subtract 16 from the amount that we started with, and we've got 5 more to look for. Then you go down here, right? 24 is now bigger than 5, so we don't do anything. No subtracting necessary. We just go left. 19 is also bigger than 5, so we go left again. And finally, we've gotten to a node where there is no left, so we know that it must be the 5th character in that, right? 1, 2, 3, 4, 5. See how that works? Pretty clever, actually. And that's what the information there gives you. Okay? What is the asymptotic complexity of search? Forgot to put that on there, I think. What do you think, Aaron?
Logarithmic.
Why logarithmic?
Because it's proportional to the depth of the row.
Yeah, it's the same idea as a binary search tree, right? You're basically making a decision here going right or left, right? And if we go one direction or the other, we've more, if this is a balanced thing, and keeping this balanced, I don't want to get into the details of keeping it balanced, but if you do keep it balanced, it's going to be just go left, go right. You're basically splitting in half each time, which is definitely logarithmic type behavior. Yeah, Charlie?
Is there any rhyme or reason as to how you put your strings into the tree?
Yeah, good question. Is there a way that you put them into the tree? You generally, yeah, there is an algorithm. Like basically you break it in half, then you kind of break it in half again, then you break it in half. But this example is like, let's say I've been adding and deleting words for a while. Like it might end up like this. But basically, if you want to create one from a giant long string, break it in half, break it in half, break it in half, all the way down, and that'll be pretty balanced. Right? So yeah, good question. OK. Any questions on searching? Yeah, Alan?
So for the balanced tree, is it each node is a word it's individually, or is it?
No, I don't think it's broken in by words so much. It's if it was balanced, it would be that each one of these is roughly, I guess the 2 to the n minus, or I guess it would be half of 2 to the n divided by, the total length of the string divided by that. So it's basically try to get the smallest chunks possible. Yeah, Aaron?
So if we were looking for the 16th character, we would go 16, and we would say 16 isn't less than 16, subtract 0.
I guess it's less than, I guess it would have to be less than or equal.
Less than 24, 0 is less than 19, 0 is less than f.
No, this is 16 here, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So yeah, you'd have to say less than or equal to. This is a one-based thing. This is a one-based list, actually. Yeah, one-based list. I thought I said that in there. No, because I say it on a different one. Yeah.
Right, so then it would, right, so you would have to handle it differently depending on whether it was one.
Yeah, you handle it differently. Right.
How you would deal with it.
Right, right. The as always, equals is always one you just make a decision when you're building it about which way you want to do it. Yeah, good question. All right, anything else on searching these things? Not so bad. All right, what other things can we do with ropes? Oh, here's the actual algorithm, right? Yeah, this one says one-based indexing up here, right? So yeah, if the weight of the node that you're looking at is less than what the number, return the right one and subtract out the amount you're at. So, and then it's just recursive. Walks you right through. Okay. All right. We can also concatenate ropes pretty easily. If you have 2 strings that are both ropes, concatenating them is really easy, right? You just take the 2. This one's hello, my name is, I guess. And if you want to concatenate these, then to connect them together, if you want to connect them like the my followed by the na, right? You just create a new node, and the 2 children are the 2 other trees that you start, ropes that you started with. Easy. Right? That's basically order 1. Although, if you do have to do some recalculating of sizes, you may have to add some more. Like if you need to calculate all the way down to here to make sure this is 9, you have to do some actual searching down the tree. So logarithmic. Okay, but it's real easy to do. So that's nice. Okay. All right. What else can we do? We can split them. Splitting's weird. This is an example. This is, by the way, these examples are all from Wikipedia. Splitting a rope is interesting. You basically say, I'm going to split it like right at the ME. You got to split everything to the right of ME. So you kind of have to find where the split part is. I'm not exactly sure how easy it is to find that part. Although I guess it would just be walking through, find that character, and then go to the next one that's, I guess it would be the next one. I guess it would be the root highest that goes right, basically. The next root up that goes right, I think is what it is. And what you do is you split it right there, and you say, OK, now I've got this piece. What's the only thing that has to happen in this piece? Like something in particular has to happen here. What do you think? Jean-Marie? Yeah, you have to update D because it's no longer got this 4 in here, so it's just going to become 2, right? OK. Now, you might want to do some rebalancing at some point, too. But OK, so that's that side. And then what are we doing with these ones? what do you have to do here? Concatenate them, right? Which means get another node and just make this the left, this the right. And that's it. Right? So we update D, and then combine the new rope for the P side, and now you've got two ropes that are now split apart. Okay? What's nice about split is that once you've got the split algorithm down, you use it for some of these other algorithms we'll talk about, which is kind of cool. Okay? So that's split. Okay? And we already talked about merge, didn't we? Yeah, concat we already talked about, rather. OK, so if we want to do insert, right? So let's say, do I actually put this in here? I'm not sure I actually put an example here. If we want to insert a string beginning at some position I, so if we want to put the quick brown fox jumps over oh, this is the quick brown fox. Let's say we want to say the quick, beautiful brown fox or whatever, right? We have to find out where the character is that we want to split, right? And then we can do a split and then two concats, and then it's back together. We basically split there, concatenate the first piece, and then concatenate the other piece back on, and you're done. So fairly straightforward. Okay, pretty good, pretty straightforward with that. OK, the other one we want to do is delete. Let's say we want to delete a piece of the string, right? If you want to delete a piece of the string, then it's the same kind of idea, right? You can accept now what you do is you have to split it twice because you're going to split it both the beginning and the end of wherever you're trying to delete, and then concatenate the resulting piece and throw out the part that you just cut out. Right? So it's the same idea. Okay, delete the new, you do a split where you want to split it, and concatenate the other two pieces together, throw away the other part. Pretty simple. Okay. All right. And then report is the last one, and it's just basically it's basically saying what does the string say, because it's not so easy to just read it out, right? Okay, you have to go through and you have to go, okay, I just do a level order traversal, or sorry, an in order traversal. Basically, I traverse down, back up, down like this, and that. An in order traversal of this will print out the string. Good? And that's all there is to ropes. Okay, a lot of text editors use it. I say a lot. A number of text editors use it. I don't know what they use for like Microsoft Word or whatever, but they might use these. It wouldn't be a bad choice generally. Although there are some trade-offs. What do you think some of the trade-offs are? Yeah. Space complexity definitely goes up, right? We've not only got to keep all the strings down here in the leaves, but we do have all these other nodes that are doing nothing, right? So there's definitely more space taken up here. OK, so that's one of the trade-offs that's not so good. What's a good yeah? What's a bad thing?
Adding a new letter onto the end is a lot more expensive than this.
Adding a new letter onto the end. Why would that be more expensive?
Because in array, you just know the index where the string ends, and you just insert there.
I see. So it's not constant anymore. Yeah. Although you might have to expand the whole string, but you're right, it's not constant. Yeah, that's a good point. So although it's pretty close to constant. In that case, it would actually be pretty close to constant even for a rope, because all you're doing is you're going to the last one, and then tagging a new node on there and putting it in. It's not too much overhead. What's that? I think it's still logarithmic. Yeah. Question.
The usual trade-off of space for time.
A lot of it's trade-off space for time. Yeah.
Because all of our behaviors now are logarithmic, pretty much.
Well, right. Most of our behaviors now are most of them are logarithmic now. Yeah, you're right. Yeah. That's a good point. OK. So here's the trade-offs that I found, right? In general, you get better insertion or deletion, right? Because you don't have to do all that moving around. You can just throw in, you just have to do the split, merge, and it's a couple logarithmic algorithms, and you're done, right? Which is nice. Now, remember, we're talking about like giant strings here. If we're talking about giant strings, you actually start to see the difference and see the issues that you're having. OK? All right. Ropes don't require this extra memory when you're actually like expanding and so forth, right? Because you're just kind of throwing new nodes on there, right? I mean, it's kind of the same trade-off you might get with a linked list, right? Every new node you never have to you just have to add a little piece at a time. You don't have to add a giant piece. There's no extra huge amount of memory you might need. Okay. Let's see. Ropes don't require large contiguous memory spaces. This is a big one, right? So if you want to look at a document that's more than 4 gigabytes big, that would be a big document. But if you had a big document like that, you couldn't keep it in memory very easily. Like there's lots of trade-offs you'd have to make. You would have to, the memory system would have to do some kind of funky stuff to enable that to happen. Okay. And this last one, this is straight from Wikipedia. If non-destructive versions are used, you basically can keep the structure intact without copying the whole piece, which is kind of nice if you're doing lots of like undo functions. You know, you type a couple sentences in Word and go, oh, no, I want to back up a little. Oh, no, I want to go forward a little. This makes it a little easier to do just because you don't have to keep huge copies of them. All right, there's lots of other ways to do undo. That's not the hardest problem in the world. Basically, keeping a list of any changes you made is probably the easiest thing to do. But this is one benefit. Okay, and then we do have disadvantages, right? We do need overall more space, right? More space here. Trade-off between the total memory and overhead, because you actually have overhead of like organizing this thing into that tree structure. Okay, and if you have big enough strings, the overhead gets less and less proportionally, which is nice. But you do have the overhead. And then you do have to have the increase in time to manage all that. You have more logarithmic things when you could be doing it with non-logarithmic methods. All right? And then, of course, these are more complex than strings. Strings are easy. There's not much to them, right? They're just arrays. This is now all of a sudden you've got some like tree structure, and you've got to make sure that everything's right, and you've got to make sure all your algorithms are right, and it's just a little more work. Once you get it right, it's fine, but greater risk for bugs in general. Okay? All right. So that's a rope. Questions on that? That's about all we're going to cover on ropes. Just want you to know about them, know that they exist. If you want to use them for a project, you're welcome to. I was trying to think if this would be a good one to use for song search, but I couldn't figure out a good way. Nothing really necessary. Maybe if you wanted to keep all the lyrics, you could, but an array works just as well for that. All right. Any questions on ropes? OK. All right. So this is the last one we're going to talk about. I actually just recently found out about these things myself, but I was talking to Professor Geyer, who you may have at some point taking programming languages or compilers class. He teaches a couple different classes in the department. And he was telling me, hey, you should go look at these things called binary decision diagrams and binary decision trees, which are interesting, especially if you're an electrical engineer. Anybody double E's in here? Anybody studying double E? A few double E's. A few. Binary decision diagrams deal with these things called Boolean functions, which you've almost certainly heard about in either regular old math class or certainly in Comp 61. Anybody taking Comp 61 right now? You guys done Boolean functions at all? Have you? Yeah, do a bunch of those things. I don't know if you do. You probably don't do Boolean decision trees, though, I'm guessing. Probably not. But what it does is it allows you to manipulate or basically store these what we call Boolean functions very efficiently, which is something that wasn't really true up until when this was created, which was like the late 80s, right? We're not talking like ancient computer science history here. We're talking about late 80s. So it's actually kind of interesting that that we didn't have these like until then. Okay. Let's go. I promised you I'd show you this little clip from Donald Knuth. I'm starting it at about 2 minutes in. So here's the story about Donald Knuth. He is, as I said, preeminent computer scientist. He's a great guy, like just brilliant. He ended up getting an article published in Mad Magazine back when he was like in high school, something. But it was about math back when they would have published something about math. Mad Magazine, who knows? But he actually, so you guys know about different bases, right? Like base 2 and base 10 and base 16 and all that. He won a high school science fair by coming up with a base based on the square root of -1. Basically, I think it was the square root of -1. That his base system was an imaginary number, which was very weird, right? But he did that, so you can go look it up. Anyway, brilliant guy. Didn't know anything about computers until he got to college. He went to well, what's now Case Western Reserve. Anywhere from Cleveland? Anybody from Cleveland here? Yeah. He went there, learned about computers, fell in love, and then all of a sudden just like took off and started designing lots and lots of algorithms, tons of different computer science like basic stuff that nobody had created yet. And he is in the middle still of writing this book. He might talk about it a little in this clip. But he wrote this book. He's in the middle of writing this book called The Art of Computer Programming. In fact, that's his title at Stanford University, is the Professor of the Art of Computer Programming. And he's been writing this book since 1962. And right now, I think it's supposed to have a total of 7 volumes. I think he's up to volume 4, right? But these are like the definitive source for any algorithm you ever want to know. Anyway, he found out about these binary decision diagrams a few years before this video. I guess a year and a half before this video, which was in the late 90s. So we didn't even know about him until then. But he has some interesting things to say. So let's see if I can do this with the sound.
Computer Science World by Storm. So there was no point in the table of contents. It wasn't until 1986 when.
Wait, no, hang on.
Right.
There, I just want to give you a little more history.
Yes to which one?
Okay, hold on. It wasn't a good joke.
Let me start out with just a little bit of history. I'm writing The Art of Computer Programming. I started it in 1962, and BDDs are somehow special in the art of computer programming because they weren't anywhere near on the scene in 1962. It's one of the only really fundamental data structures that came out in the last 25 years.
That's interesting. Since he did this in 2000, I think this was from 2008, he was saying that in the last 25 years, this is the only data structure that's really fundamental that's come out in the last 25 years, which means pretty much everything else was solved by then, but this one came out.
The germs were there, but nobody. But it wasn't until 1986 when Randall Bryant published a paper explaining what a great new data structure this was and how many things you could do with it, that they sort of took part of the computer science world by storm. So there was no part in the table of contents of the art of computer programming that had anything to do with this data structure because it hadn't existed. Now, when I say taking it by storm, his paper for many of the last 5-10 years, his paper was cited more often than anything else in CiteSeer. According to CiteSeer, his was the #1 reference paper. That's partly because you had to cite his paper if you wanted to use BEDs because it wasn't mentioned in any textbooks or very many textbooks. There were a few textbooks, but also because it's a great paper, and he had this great idea. So, without, of course, I knew about. I think it was middle of '90s when I first heard about BEDs myself, because I was interested in nights tours.
Okay, so anyway, he goes on for like an hour and 40 minutes about this. I didn't get quite through the whole thing, but this is the cutest thing in the world. See his shirt here? You can't see it on the thing here, but it says The Art of Computer Programming Volume 4, which is the one he's currently working on. Right? His wife made this for him, and she's like, "Oh." He talks about that later. Okay, anyway, so that's Donald Knuth, brilliant computer scientist, also a very good musician. Happens to own a pipe organ in his house. I guess when you're super famous and you probably have lots of money, you can afford pipe organs in your house. But likes to do that. So anyway, that's Donald Knuth. So what's the big deal about these things? These Boolean decision diagrams that he's saying took the world by storm in the late 90s or late 80s rather. Okay, what's the deal here? Well, first things first, we have to talk about Boolean functions. So Boolean functions are what I like to consider the cornerstone of computer programming to some extent. We don't actually do too many, well, we do lots of Boolean functions. Whenever we ask for a true-false answer, right, if x is greater than 7, like that's a Boolean like response, right? So it has a lot to do with computer programming, obviously. And it also has a ton to do with computer engineering in the field of circuit design. So if you're going to design a circuit, and you electrical engineers will take ES4 next semester, which, as far as I'm concerned, could be one of the most fun classes you'll ever take at Tufts, so enjoy it, the lab especially. But binary logic is kind of cool, and it's all based on these Boolean expressions. Okay? What's nice about Boolean expressions is that you use a 1 for true and a 0 for false, and it's all math after that. But it's all really simple math when it comes down to it. Okay? One not so nice aspect about Boolean functions is that it can get, I put complicated here. It's not so much complicated, but remember we were talking about how you want to avoid exponential functions, right? These things become exponential like that, right? And you'll see why in a second. Okay, so that's a problem, and that's actually one of the problems that this data structure tried to solve. Okay, so let's do a little review. If you haven't done this in a while, this will hopefully be a review, right? Couple of Boolean functions you might know about: a and b. So the and is a Boolean function, and or is another Boolean function, right? And these are not rocket science, right? These are not particularly hard, right? It's just a truth table. You guys have all seen truth tables before, I hope, right? It's all a truth table, and you just have a and b, and you enumerate all the different possibilities that a and b can be, right? And when you do a and b, it just means they're the same. And if you do, they're both 1 rather, 1 being true, that would be a and b is true. Otherwise, if a is 0 and b is 0, that's not true. A is 0, b is 1, that's also not true. 1 and 0 is not true. So that's the truth table for a and b. Okay, nothing too difficult. Or is another one, right? Or says if it's a or b is true, then the operator itself or the function is true. So in this case, everything but 0 and 0 because there's at least 1 there. Okay? What are some other Boolean functions you guys know of? Yeah, Alex?
Exclusive or.
What's exclusive or?
It returns true if both of the things are different.
Exclusive or returns true if both are different. That's one way to explain it, right? I always heard of like if and only if one is true. That's the way I've normally heard it. But yeah, that's the exclusive or function. XOR, okay? You use XOR, if you take Comp 40, you'll use XOR probably. It used to be that this got used all the time because as it turns out, if you exclusive OR two variables together, or rather, I guess the same variable to itself, you end up getting 0. And it's an easy way to make a number 0, right? You could set it equal to 0, but the exclusive OR function was always faster than equals, as it turns out. So people used to do that. Okay, what are some other ones? Yeah.
These are equivalent, so they're both the same values.
Equivalent. OK, so if they're both the same values, so what would the truth table for that be? 0, 0, 0, 1, 1, 0, 1, 1. And we're calling it equivalence, A and B. What would it be? 1, 0, 0, 1. OK, so that's another one. What other ones do we have? Go ahead.
Implication.
What's implication? OK, if A implies B, so if A is true and B is also true? Sorry, say again. So what would it be here?
That's not something you can find out from just A and B, though.
I think you can.
It can be false. It's like the logic. If A is false, it's automatically true.
Hang on. There it is. Yeah, so implication is actually one of these weird ones. I say it's weird, but it's just one of the choices. OK. If it's 0, if A is 0, it's automatically true. That's one of the definitions of it. And if A is 1 and B is 0, then it's what? False. And if A is 1 and B is 1, then it's true. So that's the one there. OK, so yeah, go ahead.
Sorry.
No, go ahead.
Finish this one.
No, I'm done.
Oh,
What's another one?
I guess you could say not.
OK, so not is an interesting one because you have to have not A, either not A, and then you can also have not B, right? And not is an interesting one because, so if you had not A, that's a good one. It doesn't even matter what B is, right? You don't even look at B. You say, right, you say it's the opposite of whatever A is. So if A is false, then that means it's true. And if A is true, that means it's false. And it doesn't matter what B is, right? You can also have not B. So it's actually, well, that's a different one too, yeah. Go ahead.
Well, there's also NAND, which only returns, I think, it returns true all the time, except when both of its inputs are true.
OK, so how about thinking of it this way? NAND is not AND. So you do and you say AND would be 0, 0, 0, 1, and it's not all of those. So it would be 1, 1, 1, 0. Right? That's not and we'll talk about that one in a minute too. OK, so we've got lots of these. How many total are there for two variables? Any guesses? 16? Why 16? Well, 2 to the power 4. Where'd the 4 come from? It is the number of permutations of A or B, but
Which is in turn 2 to the power of 2.
well, right. So it's you end up with 16 of these, and it's 2 to the power of k to the power of k, which is actually where part of this exponential business comes from, right? 2 to the power of k to the power of k can get really, really big really, really fast, right? There are big numbers in the world, and this doesn't even come close to being a, quote, big number, but it gets fast really, really quickly. So for two inputs, 2 to the k to the k is actually 2 to the 2 to the 2, 2 to the 4, which is 16, which is how many different inputs you have. And I put some of these up here. There's NAND. We forgot about just true and false, right? True and false is just, it doesn't matter what the inputs are, right? If the inputs are whatever the inputs are, it's always false. That's just called false. Right? There's also true, which is the exact opposite. And you've got all these other ones in here, and there's some weird ones. Right? If you go to, let's see, there's a Wolfram Alpha page. I think here it is. It's got lots of them here. There's all 16 written out. Let me show you these here. Right? And you've got some weird ones here, like A or not B is one of them. Right? Who knew? Like A or not B is just a function. It's because you can have a truth table with all of them. Right? There are 16 different representations when you have 0 and 0 that you could represent. Okay, so it's kind of neat. There's lots of them. So these get big really fast. Okay, you have to be a little bit careful with those. Okay, get really careful. What if we had 10 different variables? How many different combinations would we have? 2 to the 10 to the 10. 10 to the 10 is a billion. You've got 2 to the billion. That's a lot of combinations. OK? You are not going to store those combinations in. That's so much bigger than the number of particles in the universe. It's not even funny. You'd need like billions of universes to store that many like different positions, right? So we're not talking about numbers. We probably won't want to talk about numbers quite that big. OK? But it definitely gets big really fast. OK. So what's interesting about binary or Boolean functions is that you can represent any Boolean function with a combination of only a small number of those. So you don't need to remember all those different ones, right? Turns out you can do it with a single one if you really want to, okay? Called a NAND gate, which is what Alex brought up earlier, right? You can create all of the other ones from NAND, and then you can get any combination, which is really cool, right? To get not A, which we talked about, from NAND, what you do is you just do A and A NANDed together. Forget about B. Do A and A NANDed, right? And you end up getting, this is what NAND is, we talked about. If you do A and A NANDed together, it's just 1 and 0, which is basically not, right? Because 0 and 0 is a 1, and 1 and 1 is a 0, and that would give you 1 and 0. So there's how you create the not operator from a NAND gate, right? You can also do that with AND. If you want to do AND, you got to be a little tricky here. Okay, AND is a little trickier. You have to first do NAND. You do A, NAND B, and then you do not on that, which means you take the output you just got and you duplicate it, and then you do NAND again, and that gives you not, and you get A and B, which remember, this is A and B, 0, 0, 0, 1, right? 0, 0, 0, 1 if they were there. So that's kind of neat. Okay? Yeah.
How do you not again?
How do you do not? You do duplicate you do NAND on the two inputs. For you electrical engineers who might have seen this before, that's an AND gate. If you have an not, that's a NAND gate like that. That's the input. What you would do is you'd do A to both inputs, like that. You have A to both inputs.
So not
like that.
the A NAND A.
Yeah, not is A NAND A, right? Not A is A NAND A. Okay, question?
And then or would just be not a, not
Let's see. I didn't put or down. I forgot what or is. Not A. What would it be?
not a and not or NAND, not
I,
a.
I think you do the not on both the inputs and then do NAND. I think that's the way you do it, I believe.
So you do the NAND on the not of each input.
Right, that's what it is. Yeah, you do the and on that, right. The NAND on the not of each import, yeah. So anyway, so you can do this. So you could. Now, when you use these things is in these things called FPGAs, which you may or may not have heard of. If you're a computer engineer, you'll certainly hear about them at some point. But it's basically this set of NAND gates that you control, you program them to be any circuit you want, which is really cool, which is like kind of like, people thought this was the wave of the future, but it turns out it's a little slower than you might like for some other things. But it's still a pretty neat concept. You just have a whole bunch of NAND, what we call gates, on this chip, and you say program to do whatever to be a circuit that has the following outputs, which is really cool. Okay, so you electrical engineers will get into all that when you get there. Okay, but we don't normally use NANDs for the analysis that we're about to do. What we normally do is, let's see, this was the NAND. Oh, let's see. We normally limit ourselves to 3 of the very basic ones, not, which we talked about, and an or. Okay, using those 3, you can also represent any of them. Of course you can, because you can represent them all with NANDs, but you can represent any Boolean function using those 3. Okay? And this is how we represent A, not A, by the way, 2 different ways. One is with a little line over it, which just says not means not, or we put a little apostrophe next to it. It also means not A. Okay? All right, so we're getting there in this stuff. Here's an arbitrary function that we have, and by the way, did I put this on the other one? Yeah. The shortcut for this is it looks like you're multiplying A and B together. That's and. And by the way, if you do it in binary, multiplication really is like it's very similar to multiplication. Like when you multiply together, I guess it's not exactly, but it's fairly similar in the sense. But anyway, when you do A and B, you just put A next to B, and that means A and B. That's another shortcut. A or B is you have a little plus in there. Okay. So what does this arbitrary function mean? Well, it means not x1, not x2, and not x2, and not x3, or x1 and x2, or x2 and x3. Okay. Yeah, question?
On the slide before,
Yeah.
is the middle one correct?
Did I do that one wrong? Oh, you did do it wrong. Thank you. Maybe that's why it looked funny. How about it should be 0, 0, 0, 1. Is that better? Yeah, now it does look like multiplication, doesn't it? Yeah. All right. And then the other one's all right? OK, thank you for that catch. Good catch. OK, so back to this arbitrary function. We've got this arbitrary function, and it's got 3 variables in it, x1, x2, and x3. OK? And there's 8 different solutions to this. Now, this is not, with 3 variables, how many different combinations of just those 3 together could you make? We already said that was going to be 2 to the 3 to the 3, right? Which would be a lot. 2 to the, what is that? 2 to the 9th, I guess, right? There's a lot. 500. What is that? 512, or maybe it's.
2 to the 27th.
Oh, sorry. 2 to the 27th. No, it's 2 to the 3 to the 3.
3 to the 3 is 27.
Oh, 3 to the 3 is 27. Thank you. Yeah, a lot. So you can do a lot of stuff with just the 3. But what we're talking about now is the solutions to this if x1, x2, and 3 were either 0 and 1. Okay, does that make sense? So let's say they're all 1. Okay, let's see if we can figure this out. If they're all 1, then not x1 would give you what? 0. 0 and anything gives you 0. So this part's 0. Okay. 1 and 1 gives you 1. So this part's 1. Well, 1 ORed with anything else gives you 1. OK. So, but there are 8 different possibilities here. Everybody buy that? Yeah, Charlie?
So is there like an
You always do the ands before. You do the nots first, then the ands, then the ors.
Yeah, so
But
what I'm asking is, if you switch the x1 and x3, does that matter?
if you switch the x1, no. If you're talking about what would that be? That would be associativity. That does not matter. Yeah. Yeah. Okay. Neither does commutativity either. So you can move them all. You can move the pieces all around as well. Okay. Yeah. So it doesn't matter in that sense. Now, your computer might think differently, because sometimes we do what's called short circuit evaluation, where if you're doing an and, like if A and B, and the first part is false, it won't even look at the second part. But you can use that to your advantage in programming at some point. Okay, 8 things. Yeah, Jean-Marie?
What's a solution? Because the answer can be either 1 or 0.
Right. Right. It can be either 1 or 0, but given the inputs of 0, 0, 0, 0, 0, 1, 0, 1, 0, I'll show you.
Okay.
I think the next doesn't even, it's on, no, I don't have it right here. But it just means that you would have the whole truth table like this. You'd have the truth table like this. You'd have x1, x2, x3, and it'd be 0, 0, 0, 0, 0, 1, 1, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, 0, 1. And then what would the solutions be, right? Yeah, this is the 0, 0. We just did the 1, 1, 1, 1. 1, 1, 1, 1. And we could do the 0, 0, 0 choice as well, right? That's how many different solutions there might be. Now, these are either going to be 0 or 1, so they will all converge to either a 0 or 1, sure. OK. So if we had 1,000 variables, what would our number of solutions be? Just the solutions, right? For here, we had 2 to the 3 solutions. So for here, we'd have 2 to the how many? 2 to the 1,000 solutions, right? You're not getting into quite this territory, but you're getting into, you can't represent 2 to the 1,000 anythings. It's impossible. There's just not enough particles in the universe to do that. OK? So we've got to figure out something else. We might want to represent this function somehow such that we can easily figure out what the solutions are. Well, that's where these binary decision trees here. We don't want to represent 2 to the 1,000 places. You can't even do it, right? So what we want to do is we want to say, OK, we want to actually, and this is another solution here, we want to come up with some way to represent this. Here is one way to do it. OK, you come up with this, what we call binary decision tree. OK, and what it says is, start at the first variable, and then branch off. Dotted lines mean zeros, basically, if it's a 0 in that place. And solid lines means true. OK? For x1, we've got 2 choices for x1, false or true. And for each x2, we've got 2, false or true. And you see how this branches out? This is where the exponential nature of this comes from, because it just branches right out into this big tree here. And here's the actual solution. Now, Jean-Marie, does this make sense for the solution now? These are all the ones. This is the one we did before. If you look at 0, 1, 1, let's look at how we would figure out this. 0, 1, 1 should go to 1. So 0, 1, 1 means x1 is false, x2 is true, x3 is true, and it ends up at a 1. See how that works? That's how these binary decision trees work. OK? It's not quite efficient, though. Right? We still need 2 to the n minus 1 nodes here to represent the 2 to the n different solutions. Right? I mean, you're still going to have to do this because you're still going to need, because you're enumerating the whole thing. OK? Well, what can we do about that? All right. We can start merging things that don't actually, like that are what we call isomorphic, the same. For our intents and purposes, isomorphic means the same. So watch this, right? Any node, merge any subgraphs that are the same. OK, this one's not a great example because there's not that much going on here. But for x3, these two x3s, notice how the ones are the same. By the time you get to this x3, does it matter what x3 is? Because at this point, if you've gotten to this node, it doesn't matter what x3 is. You're going to get a 1, no matter which path you take. Right? They both lead to 1. And let's see if that makes sense. 1, 1. So if it's 1, 1, notice if x1 is 1 and x2 is 1, and x1 is 1 and x2 is 1, it doesn't matter what x3 is. They both go to 1. Does that make sense? See how that works? OK, so we would merge these. right? And we'd merge these two, these ones as well. Okay? So you merge those, and you also eliminate any node whose two children are isomorphic. Okay? In other words, so in this case, the x3 here doesn't even need a b here. You just basically replace this x3 with a 1 and get rid of the rest of it, and there's your answer. Okay? So what does that mean? Well, we can merge some of these things, right? First things first, we can do this. We can say, OK, x2, we don't even need those x3s over here. They're merged, 0 and 1, because it doesn't matter anymore, right? And the other thing we can do is we can actually just go to one set of 0s and 1s. Okay, now it's a little harder to draw these, right? You can't use straight lines anymore, right? Because of the way you have to, like, it's not like a nice graph anymore. I mean, it's not like a nice tree anymore. It turns into a graph, really. And how does it turn into this graph? Well, x1, what happens is x1 to x2. So if it's 1, 1, you get a 1 out of it. 1, 1. We don't care about x3. 0, 1, 0 goes to 0. 0, 1, 0 goes to 0. But 0, 1, 1 goes to 1. So that one needed to stay there. Do you see how this works now? Now notice, OK, for this graph, or for this diagram, we haven't compressed it too much, right? We've taken out a couple nodes here. But it's definitely a little bit smaller. If you're talking about huge graphs, this gets really compressed, which is cool. OK, it gets really compressed. What we call these are reduced order binary decision diagrams, ROBDDs. But when you talk about binary decision diagrams, you just call them BDDs. You don't worry about the fact that you say, OK, if it's a reduced diagram, it's already reduced. Couple things. One thing I didn't say on here, the order of these variables matters. You have to go, if you go from x1, you can't go x2 and x3 unless this one could be differentiated. You can't like move an x3 up here and then go back down to x2. You have to do them in the same order. Whatever order that is. Okay, whatever that order that is that makes sense. Okay? And what you can do with these is you can compress this down. For the 8 case, it doesn't make, or for this case, there's 8 things, doesn't make that many, like that much sense to compress it, but you can. If you're talking about a 1,000 variable one, most of those, shoop, compress right down, which is kind of cool. Okay? It depends on the ordering of the variables. Notice back here we went x1, x2, x3. Up here, if you go sort of different type of, I don't have the, this is on the Wikipedia page. I could show you this too. You can go look at the actual function. But if you go x1, 2, 3, 4, 5, 6, 7, 8, look at how nice and small it is. If you try to go x1, 3, 5, 7, 2, 4, 6, 8, it blows up to a very ugly type of graph. Figuring these out is a hard problem. Okay? In fact, it's called what's called NP-complete, which I know some of you guys have thought about before. And you will learn that in a couple other classes. In particular, you'll learn about that in computation theory in a couple years. Yeah, Aaron?
Like if you wanted to have a computer make one of these, it would basically have to like, make the long form one and then look for compression, like ways of compressing it, and then, or like.
Let me show you how we would do it.
Then like try all of them to figure out the best order.
Yeah.
So we just get like it would be like.
Well, you do have to try all of them. Yeah, you're right. You have to try all of them to do it. But here, well, it's not too bad. I mean, for 10, it's not for this many, it's not that bad. In fact, there's a program I'll show you in a few minutes that does it for you. We're going to show you how to do it. I'm going to show you right now how to do it kind of in a very simple way, and you'll see how it works. Okay. So we're going to try to come up with the binary decision diagram for the following function: A, B, C, A and B and C, or not B and D, or not C, D. 4 variables here. Okay, I call them A, B, and C, D instead of the X's. Easier to type anyway. And we're going to use a special ordering. We're going to say that we're going to do B first, then C, then D, then A. Why? It's just it makes it a little easier. Okay? Here's how you do this. Okay? And you people who are taking double E classes, you'll get used to this sort of analysis when you do it. Okay? What you do is for the first variable, B, that we're looking at, what you do is you compute what we call the cofactors of this. Figuring out cofactors is easy. You look at the original, and you say if b appears in here, we get rid of b but keep that term. So ABC just becomes AC. If you've ever done partial differential equations, it's very vaguely similar. If you haven't, don't worry about it. And they're ugly, so you don't have to do partial differential equations, don't. But see how ABC, with respect to b, you just get rid of the b and you leave a and c. Okay? B prime or not BD, well, because it doesn't have the actual b in there, this whole term goes away. The b prime says you're going to go away. So that one goes away. And then C, not C and D, there's no b in there at all, so that remains, that whole term. So the function of b with respect to b, the function with respect to b is going to be AC and C, not CD. You see how that works? It's not that hard. Look at it again and see. Yeah.
Sorry, so just for clarification, so when there's the not of that variable that you're reducing by, then that's eliminated.
Eliminated.
If there's nothing in there, then that remains.
The whole thing remains, yes. And if it is there, not the regular version, then the rest of it remains. It reduces it a little. Okay. All right. So that's all you have to do. Okay. AC, and for the f with respect to b, it becomes AC and or not CD. If we do the exact opposite, which is we find the cofactors with respect to not b, it's exactly the opposite. If not b appears, we leave it. If b appears, we get rid of it. So ABC goes away, not BD just becomes D, and C prime D remains. Okay, so those are the two functions. That's the first thing you do. Yeah?
If you have a term where the thing is present and then the rest of it remains.
Like which one?
If we had just like plus b on the end, then that would
become 1. Plus 1, yeah.
Plus true, which would just make the whole thing true.
Yeah. Yeah. And we'll see that happen in a minute. You'll see where that happens. Okay. So we've got that now. We just start creating this little diagram. Okay? All right. Then what we do is now we've got the branching effect happening here. We have figured out function of b. Now what we need to do is we need to do that function with respect to c and not c. So it's the exact same calculation, except now we're just doing c and not c. Well, the function b with respect to c is going to be a, because this one stays and this one goes away. And the function with respect to not c is just d, because this one goes away and this one remains. Do you see how that works? Okay. And you do the exact same thing for b prime. It's going to be, the original we had before was d or not cd. And when you get when you do this, you get b prime c. Well, that one goes away, and this one stays, and this one goes away. And then for the b not c, you've got, let's see, same thing. That one remains, and that one also remains. But what are two things ORed together? They're the cell itself, right? Two things that are the same ORed together gives you that. So we've got three things here that all became d. This one, and this one. The only one that's left over is this BC, which is up here. So what this becomes is all three of these, let's see, the B not C one, that's here, is a D. And this one and this one are also Ds. These are now all the same. We're going to be able to start merging like I talked to you before about. Yeah? I'm going to show you that right now.
Will we be asked to, on the final, will we be asked to just convert the equation to a tree, or will we be asked to merge it as well?
I haven't decided yet. I'm not going to make it hard. If this is like, I see a lot of people who are like, what's going on? But I'm not going to stress too much about this, right? But yeah, but I'll give you an example of the thing you might need to know. Yeah.
Just a quick final question. You brought it up. Is this final going to be more concept based or more coding based?
Haven't decided yet.
Okay.
Probably a little bit of both. Kind of like the other one. Okay, so what we've done, hang on, Charlie. What we've done is we've now said this, and this are all the same. So combine them all into just one function, and now we've got a much smaller graph already, right? And all we need to do now is do this one and this one. Well, it turns out this one's actually easy. Let's see. This one, B, is A. We now need to do, I think that should have been BC actually. We need to do it AC and CD. Well, this is the same one. Sorry, this is the same one. Next one we do is BC with respect to D now, I believe is what we're doing, right? With respect to D. That one just becomes A, which is nice. And the other two become 1 and 0. OK, so we're going to get a 0 and a 1, and that one's still going to be the same as before, because, or you could have made it A if you want. Don't worry about a lot of the details of this. And then finally, we do the same thing again, and we end up combining. We can combine things up here again, and we can combine them. Well, actually, we don't really combine anymore, but you end up with the final result here of your binary decision diagram, which we did just by doing that, by finding those cofactors, and we combined it right down. Okay? Aaron, does that make a little more sense as far as how we do it? If you know the order, it's easy to do. Not that hard to do. Yeah?
Is there a uniqueness guarantee?
There is a uniqueness guarantee. This is, I say a uniqueness guarantee. It will give you the right answer. So it's not going to be, it may not be the minimum one. Because remember, you can have this, depending on the order of the variables, you can have two much different ones. But it will be correct. Let's put it that way.
And the two values, wait, on the previous slide. Oh, wait, one back. The two values there, F, B, C, will be whatever value we fed in for A and
yeah, that's going to be when we solve it with respect to D again, and then when we redo it with respect to A again. If you go back and look at the slides, it'll become a little more clear. It's not that hard. It's just kind of an algorithmic process. Yeah.
What would be like a use for this?
Yeah, good question. What would a use be for this? Well, when you're doing let me jump ahead because we're almost out of time anyway. Let me just quickly. I'll answer that in about 2 minutes. No, 1 minute because we've got 2 minutes. So once you do this, there's the truth table. If you wanted to check this, you can, and it does work. I checked them all. Right? Let's pick one. This one, 0, 1, 0, 0, should go to 0. So if we start at B, which was 1, B goes to 1, C goes to 1. Is this the one I picked? 0, 1, 0, this one. C goes to 0, sorry, C goes to 0. D goes to 0, and that's it. And it didn't matter what A was, and that would be 0. So you can figure this out, it actually works. Now, this is many fewer nodes than it would have been had we done all of these out. Right? So that's kind of the benefit of these things. Now, there's one online if you want to look. I don't have time to show you right now, but it's online, and it will do these for you. And it will give you the big one and the smaller one. It'll figure out the minimum one for you, which is cool. And here's why we do them. So computer-aided design for circuits uses this stuff a lot. Okay, what it does is it will use it to create circuits, because what you're trying to do with circuits is circuits are by design binary functions. Boolean functions, and you're trying to get from point A to point B with a circuit. You throw it into one of these, and it figures out the best way to go, the best smallest circuit possible, which is kind of nice. It can also be used to verify human-made ones. So if you're a human and you design some of these and don't use all this fancy computer stuff, it will verify that it is correct. So that's nice. Okay. This was on Wikipedia. I'm not sure exactly what this meant, or what the use is, but you can use these for private information retrieval. And this is kind of cool. You can retrieve information from a database without revealing which item you actually asked for, which is pretty cool. So it's a nice, secure way of doing things. OK? All right. Questions? Yes?
Are either of those things on the lab?
No, the lab is on graphs, just plain old graphs, traversing graphs. And there is a pre-lab. Don't forget to do the pre-lab. See you guys later.